Again, this is structural analysis and design made fun and easy. This is video, changed it, video 3 of 4 of reinforced concrete brace short column and square pad foundation design to BS 8110. That's UK concrete standard. So this is a structural analysis and design made fun and easy. Reinforced concrete brace short column square pad foundations designed to BS 8110 UK, which is a UK concrete standard. This is a very simple case, very simple pad foundation just to get started. This is part 3 of 4 in this series of the videos. And please like the video and subscribe to the channel. Please donate if you can to let me make more videos like this. So in part one we went through the columns, the loading, the capacity of the column with the reinforcement in the column. Then 2 I did the bearing capacity check. Part 2 was the bending moments in the pad foundation and the design of the reinforcement. So that was in video number 2. This is video 3. So now we got to determine the shear stress in the base at a line across the base of 1 times the tensile steel effective depth from the face of the column. So what I've done is I just drew in. Let's start with this. Start with this up in the corner. So this is the pad foundation upside down. So here's the column. Here's the pad. In the red, that's the bearing pressure on the foundation. From before, we found that was 260 kilonewtons per meter squared because it was 1040 divided by 4. So that's 250 plus 10, so that's 260 kilonewtons per meter squared. So over the UDL over the bottom of the pad foundation, 1040 divided by 4 is 260 because it's 250 plus 10. So there's a section through the pad foundation. That's the column. It's upside down. That's the base. So what we need to do first of all is find the shear force at a distance of D from the column face. So as previously mentioned, it does not seem to say the column dimensions. So I am now having to make an assumption that the column is say 300 by 300 millimeters square, because otherwise there's no way of you just have to do it from D from the center of the base, but we don't know what the column dimension is. So it must be more than 0. So I'm just going to say it's 300 by 300. So therefore, first of all, find the shear force at a distance D from the column face. So let's say the column face is 300 times 300 millimeters. So the half of 300 is 150. So that means the column is 150 each side of the center line. So and D is already found out, effective depth of 340. So we need to find the shear force at 1. So let's say it's half. This is half of the width of the pad is 2 divided by 2, which is 1. Find the shear force at 1 minus. So we need to find it at a distance D from the column face. So the column face from the center is into this one side of the pad is 300 divided by 2, which is 150. Then plus D, find the shear at that position of D plus 150. So D is 340. Column face is 300 divided by 2. So it's the total distance from the center line of the pad to where we want to find the shear force is 340 plus 150. That's 490. So from the left hand side of the pad, so refer to the Idolized shear force diagram as shown on the bottom of the left. So this is how I envisaged the shear force as acting on the base. So because it's a UDL, we've got 0 here, then it goes steadily to the center, then you got the column, then it goes, so the column reaction is 1040, and then it will just go back on the other side to 0. So we want to find the shear force at where the distance is 490 from the center line. So that distance from the outside edge to the center of the shear force, where we want to find it, is 510, because it's 1 meter minus 0.490, 510. So the UDL is 260 at the base. So the shear force per meter width is 0.510 times 260 is 132.1 kilonewtons per meter per meter width. So here I just tried to show that the I haven't drawn the whole thing 3D, but it's just to show like the pad has got 2 dimensions. This is the width, like this is the length, and there as well. So instead of designing instead of finding the shear force across 2 meters of the base, just divide it by 2. Otherwise, it would be instead of it being 260. Instead of it being 132.1 kilonewtons per meter, it will just be 264.2 kilonewtons altogether, because it will be half of 1040 is a total reaction, then divide that by 2 will be 520. So then it will just be 0.510 times 520. That would be the shear across that entire length. Say this section is a meter wide, so we're taking like a section across there. So therefore the stress, so the stress is actually V. The shear stress, that should be little v. That should be V is equal to the shear force divided by B times D. So it's 132.1 times 1,000 divided by 1,000, that's 1 meter wide, times 340 was 0.39 newtons per millimeter squared. So therefore the so the shear is 0.39 newtons per millimeter squared, because just double checking it. Here I've just done a diagram to show you. I tried to do a 3D diagram. It's a bit hard on Microsoft Word, but here's the pad foundation. It's 2 meters by 2 meters. This is 1 meter wide. This is 1 meter wide. This is 1 meter wide. So we've got to find the shear force at 0.49 from the center of the base, which is the same as 340D from the column face. So along that line, that distance there is 0.49, and this distance here is 0.51 meters. So the shear force is equal to the shear stress, the shear stress equal to 132.1, which is 0.510. Times 260 is 132.1. Yeah, because it's increasing towards as you go from the edge of the foundation, the shear stress must be 0. It's got to be 0 there, and it must be the maximum here. So therefore, you times it by 0.51, because it's going towards the collar, not away from the collar. So then done a diagram of the section here. That's 1,000. So the shear stress is equal to 132.1 divided by 1,000 times 1,000 equal to newtons divided by 1,000 wide times 340 deep. That is equal to 0.39 newtons per millimeter squared. So that is basically it. That's just show that depth of that foundation is 400. That's 2 meters along that side, 2 meters along that side. So half is a meter. This is 1 meter as well. This is 1 meter. I'm just going to find the shear stress by looking at 1 meter wide section. They basically have 2 strips of 1 meter because it's 2 meters wide, and then the load is 1,040. This is equal to 132.1 kilonewtons per meter wide. So if you could do it over 2 meters over the entire width, it would just be 264.2 kilonewtons over the entire width rather than 132.1. So that's the end of part. This is part 3 now. So this is the end of part 3. Please see part 4 is just checking on the punching shear of the column. That's fairly easy, so I'll go over that in question in part 4. Yeah, please like and subscribe to the channel. Please donate if you can. Thanks for watching.